see if you can prove that each of these functions is computable. So what you'll be doing is building Turing machines that compute each of these functions. You want to make sure that the Turing machines are guaranteed to halt. And you can define these Turing machines using formal definitions, using implementation level definitions, or using high-level descriptions. So any of those is OK. But I want us to get some more practice writing Turing machines, in particular for these three functions, where C is supposed to take a string x and map it to y, where if x is a binary representation of a number n, y is going to be the binary representation of 2n. So how is F1 related to it? And I believe we're in this part of the room at the moment. What's F1 doing that helps us with C? Yeah, go for it.
Because by adding a 0 to the end of the string, we are bubble the function.
Cool. So in F1, notice that what we're doing is adding a 0 to the end of the string. That's what the notation x0 means. It's a concatenation of x with a 0 at the end. And by thinking back to CSE20 or CSE30, we remember that adding a 0 at the end of a binary representation means doubling the value. And so that's what we want to do here in C. Okay. All right. So let's build the Turing machine that does that. We need to build some algorithm, our black box that we're going to build just now, that takes an x and outputs x0. And the black box is going to be implemented by a Turing machine here.
Do you just travel right until you see the first blank cell and then write it?
Cool. So you're describing how we'll do it on the tape. So you're giving an implementation level description, which is to travel right until the first blank, write a 0 on that blank, and then halt or accept. Cool. So F1 is the function. We're building the machine that computes it. So if we want to think about actually the formal definition of this Turing machine, it's small enough that we can actually write it on a single slide. We can imagine that this implementation level description is telling us that if we start with x on our tape and we have a blank at some point, right? So we've got some 0s and 1s if that's our alphabet. Let's assume that sigma here is 0, 1. And then after the last character of x, all of the cells in the tape will be blank. And so this idea of travel right until the first blank and then write a 0 at that blank and halt will tell us to start with our tape head in the leftmost cell, which is what it always does, go to the right until we get to the blank, put a 0, and complete. So we can write down the state diagram where in our start state, Q0, as long as we're reading 0s or 1s, we don't touch the tape. So we write back the symbol that we read, as in don't change it. And we keep traveling to the right. But as soon as we see a blank, then we write a 0. And we're going to halt. So it doesn't really matter where we put our tape head. We can go right or left. Who cares? Let's just do right. And then we're going to halt. And I would recommend F2 describing its Turing machine using an implementation level description. So thinking about how your read-write head moves along the tape backwards and forwards, perhaps, and how you make it so that at the end of the computation, what we have on the tape is the original string and then copied again.